This is the Physical Science Section 17.4 lesson video, and so as always, if you want my videos in one spot, then just subscribe to my channel. So sound waves is what we're going to talk about today. Sound waves are longitudinal waves that travel through a medium. So transverse waves travel like this, longitudinal waves travel like this. Many behaviors of sound can be explained using a few properties: speed, intensity, loudness, frequency, and pitch. So let's talk about this. So in dry air, the speed of sound is 342 meters per second and 20 degrees Celsius. In general, sound waves travel fastest in solids, slower in liquids, and slowest in gases. And this is because the particles in a solid are closer together than those in liquids and gases. Because remember, those particles need to bump into each other to allow that wave to pass through. So because the particles in our solid are closest, the sound will travel fastest through the solid. Intensity is the rate at which a wave's energy flows through a given area. Sound intensity depends on both the wave's amplitude and distance from the sound source. So even if a sound wave is really, really, really loud, if you're far enough away, you won't hear it. So for example, if there's a really loud noise in Europe, I'm so far away, I'm not going to hear the sound. So the decibel, which is dB, is the unit that compares the intensity of different sounds, and loudness is the physical response to the intensity of sound. So here's some example of decibels. So for example, 88 decibels we can tolerate for about 4 hours without having any pain or hearing loss. Whereas once you go up to 100 decibels, we can only withstand that for about 15 minutes. But once you go up to like 112 decibels, you have less than a minute before your eardrums might burst, you're going to have some pain, you may be disoriented. Loud noises sometimes will make you disoriented. Pitch is the frequency of sound as you perceive it. That's why some people can't sing well. They sound off pitch to us, but to themselves, the way they perceive it is they sound fine. High frequency sounds have a high pitch, like for example, my voice has a very high pitch. And low frequency sounds have a low pitch. So like a man's voice would have a lower pitch because it has a lower frequency. Ultrasound is a sound at frequencies higher than most people hear. So when you go get an ultrasound, you can't hear it, but they can use those sound waves to create a picture of what's inside. So for example, they use it to look at babies, they can look in your blood vessels, look at some of your organs, things like that. Ultrasound is used in a variety of applications, including sonar and ultrasound imaging. So sonar is a technique for determining the distance to an object underwater. So sonar stands for sound navigation and ranging. So what happens is it allows sound waves to go, and once they hit something, they'll bounce back. So see, most of the waves, once they hit the bottom, they take a while to bounce back. But see, a little bit is going to hit this fish, and notice it bounces back before the waves that hit the bottom of the ocean floor or the lake floor, depending on what this is in. And so the boat's radar will note the fact that, oh, there must be something right there because those waves are coming back faster. Some animals use sonar. For example, bats, they can't see well, so they use sonar to identify prey and things like that. The Doppler effect is the change in sound frequency caused by motion of the sound source, motion of the listener, or both. So as a source of sound approaches, an observer hears a higher frequency. When the sound source then moves away, the observer hears a lower frequency. So as something is moving, like if you look at this car, the waves in front of it get kind of bunched up. So here we go. And so it starts driving, the waves get bunched up, and so if the waves get bunched up, they have a higher frequency. So to us, it's going to sound a little different. And if you look behind the car, again, instead of getting bunched up, the waves get a chance to spread out because the car is moving away from that area. And so that has a lower frequency. So that's what happens when like an ambulance or a siren or something passes by. When it's heading towards you, you hear that high frequency, that wee-oo, wee-oo, wee-oo. But the second it passes you, it's just kind of like wee-oo, 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 wee-oo. Like it immediately changes frequency. And that's because in front of the object, the waves are pushed together. So you hear high frequency. And behind the object, the waves are spread out. And that's just Doppler effect. So, section 17.4 assessment. List 5 properties used to explain the behavior of sound waves. Well, we have speed, intensity, loudness, frequency, and pitch. Speed, intensity, loudness, frequency, and pitch. Name 2 uses for ultrasound. Well, we use it in the medical field through ultrasound imaging and sonar. Ultrasound imaging and sonar. What is the Doppler effect? Well, the Doppler effect is a change in frequency due to motion. So remember, we talked about as it's moving, the waves in front get bunched up, high frequency, the waves in back spread out, low frequency. And then last one, if workers at a distant rock quarry are blasting, why can you feel an explosion in your feet before you hear it? Remember, sound waves travel fastest in solids. The ground we stand on is a solid. So the sound waves can travel through the ground faster and we can feel it before it can travel through the air and we can hear it because, of course, air particles are spread out further. So hopefully now you know a little bit more about sound waves.